natural disasters, climate change, overcrowding. Big problems demand even bigger solutions. It's a new era for engineering. We can build our way out of anything. In Washington, D.C., a fleet of intelligent self-driving pods could take cars off the road. This is mega engineering. Imagine a city with no cars and no traffic, where a personal ride is only the press of a button away, where you don't drive your vehicle drives you. Washington, D.C. is the most congested city in the U.S.
The traffic situation in Washington, D.C., in a word, it's bad. Probably the biggest reason why we have this congestion is that we have an awful lot of people going into and out of D.C. at certain times.
That's because D.C. is a company town, dominated by a single employer which uses a lot of manpower, the government. For civil servants and contractors alike, business hours tend to be 9 to 6. Each day, over 1 million cars surge in and out of downtown Washington during rush hours, causing traffic jams that waste over 100 million driving hours a year. And it doesn't help that the layout of downtown D.C. inhibits the smooth flow of traffic. For that, drivers can thank the Founding Fathers. In 1791, George Washington hired French architect and Freemason Pierre-Charles L'Enfant to design the nation's capital. L'Enfant designed the city to be a model of order and elegance.
L'Enfant, as an architect and a designer, was not clearly, at that time, a traffic or transportation planner.
His plan detailed specific locations for government buildings and designed streets not to move traffic through D.C., but to maximize sight lines to the city's iconic architecture.
So it really was not something that was thought about from a traffic point of view, and clearly not what we have in the 21st century. You can look down Pennsylvania Avenue from the White House to the Capitol to have that clear view and vista. And so as you start to do those types of things, you end up with a somewhat obtuse street system that simply creates challenges for commuters and visitors.
L'Enfant never dreamed the population would boom from 10,000 to nearly 5 million, and he surely didn't anticipate the automobile.
You have a layout that was designed by people in the 1700s that's supposed to suit the 21st century. It was never designed to suit millions upon millions of automobiles. They're alien invaders, in a way. They're slowly devouring their environment.
Nowhere is that more apparent than on Kenilworth Avenue, where a costly highway expansion project is underway. It's a convoluted process and a monumental undertaking, but it may not make a difference. The traffic load here has dramatically increased in the last 15 years, and it's still rising. If the trend continues, these 2 additional lanes could be jam-packed within a few short years. Because of the high cost and limited value of road expansion in densely settled cities, transportation engineers are arguing for a radical departure. Some are proposing an idea that seems like science fiction. Eliminate cars from dense cities and replace them with personal rapid transit. or PRT. Electric self-driving vehicles, safer than automobiles, and faster than mass transit. Riders will enter a station and select their destination. A passing pod will then immediately stop to pick them up and drive them directly to where they need to go. High speed, non-stop, and with no driver.
The idea is that a pod car moves you through the city with the same privacy and convenience of an automobile, but without all the problems that are associated with cars. It's essentially an automated taxi system that moves you anywhere in the city.
Automobiles running around Victorian designed cities is just hugely inefficient. There's tremendous room for efficiency, and the pod design speaks to that need for greater efficiency.
Personal pods will be an upgrade on the car in almost every way. They will draw energy from a power grid, which can include renewable sources of energy like wind and solar. They'll be built out of lightweight plastic and composite materials, making them more energy efficient. And most important, they will be fully automated, virtually eliminating accidents caused by human error. Safer than cars and cheaper to build than roads are railed, the PRT is the holy grail for transportation engineers. And for those who swear by what some call the pod car, their mecca is a little town 3 hours west of Washington, D.C., Morgantown, West Virginia, where the only working pod car system in the world has been serving West Virginia University students for over 30 years.
West Virginia University has so much to offer. Great academic programs, outstanding faculty, and an awesome student rec center.
Don't forget about the one-of-a-kind personal rapid transit system.
That's me!
The Morgantown PRT is a fleet of 73 driverless pods, which taxi riders non-stop around campus over 8 miles of guideway track.
The Morgantown system is the closest system in existence to a pod car system. It had some of its origins with President Nixon in that he wanted to do something along the lines of the space effort.
Morgantown was chosen because West Virginia University has 3 distinct campuses, and it was just needed to provide that connection, but also was needed to see if PRT could work in a public transit operation.
To use the system, a passenger simply swipes an ID card. The system diverts a passing pod. Once aboard, it's a non-stop ride to the final destination.
Morgantown is the safest transportation system in the world. It's in fact the best public transit you've never heard of.
The system drew public attention in its early years, when it was plagued with problems and delays. Design changes to the pods caused the budget to balloon from $11 million to over $120 million, and the project was nearly killed before it even got off the ground.
About 1973, I was still a student here at the university. There was talk about tearing the system down. They had budget overruns. That's when they were having some design issue problems with the guideway, with the vehicle.
Designers belatedly realized that snow could pose a significant problem in a town that receives an average of 30 inches each year. So they decided to install a heating system beneath the guideway surface to ensure that the PRT would run in even the worst weather conditions. Their foresight is paid off when heavy snowstorms paralyzed the city.
While motorists were literally spinning their wheels in the street.
The PRT is often the only transportation system left moving, impressing even its harshest critics. But the Morgantown PRT has never lived up to the promise that it would be fully automated. For starters, the hardware that controls it is a pair of 20-year-old computers, state-of-the-art in their day, but never up to the job. And today, the system still requires constant human troubleshooting. But despite its troubles, riders have always loved it. In the mid-'80s, when the experiment was scheduled to end, Congress voted to keep it alive. Today, it moves 15,000 students each day, and the cost is modest. 50 cents for Morgantown citizens and free to all students. And after all these years, the Morgantown PRT has maintained a perfect safety record. 70 million rides and 0 fatalities. Performance like that in Washington, D.C. would save hundreds of lives and millions of dollars a year. Morgantown points the way, but the DC system will have to be much more sophisticated. The personal pod network will have to be 250 times larger, with hundreds of stations and nearly 1,000 miles of guideway. And designers will need to develop truly safe, personal, and intelligent self-driving pods. Some engineers believe that the best way to tackle these problems is to build the system in phases. The first step would be to build parallel to one of Washington, D.C.'s busiest traffic corridors, the highway that connects downtown with Dulles International Airport. In the second phase, the pod car system would be expanded to include pods on streets, and a lightweight suspended guideway infrastructure capable of bypassing congested areas and reaching every block of the city without the cost or disruption of major construction. If DC succeeds, it will be a model for personal pod systems worldwide. But the road ahead is long, and traffic in the capital will have to get worse before it gets better. The push to make the auto obsolete will begin on the outskirts of Washington, D.C., where an army of construction workers will build guideways for high-speed, self-driving pods, running between Dulles Airport and downtown. A pod system here would take thousands of cars off this heavily trafficked highway and relieve the crowded city. It would be a complex and difficult undertaking, though perhaps made slightly easier with help from lessons learned at a similar project already underway in England. At London's Heathrow Airport, vehicle testing has just begun on the world's first truly personal pod system. It's part of a radical plan to reduce ground traffic at the world's third busiest airport. At Heathrow, over 1,000 planes take off and land each day. 185,000 passengers stream through its 5 terminals, coming and going in a daily influx of 50,000 autos, 2,000 train cars, and a fleet of 200 buses cycling in and out of the city. Taken on its own, Heathrow's massive Terminal 5 is actually busy enough to be counted as the world's 10th busiest airport. In the first 2 years since the new terminal opened, Heathrow tried beefing up public transportation to ease pressure, but with limited success. Buses and trains just aren't ideal. Their schedules are too inflexible, so they can't adapt to sudden shifts in demand. Finding a silver bullet to end Heathrow's traffic woes proved elusive. Until 2005, when Heathrow administrators were approached by ATS, a small company with an unlikely solution to the airport's traffic crisis.
BAA came to this about 5 years ago. ATS, the company that are supplying this system, came to us and said, we think this would be a really good solution to some of your problems at the airport. And after a year or so, we started to believe them.
Their idea? The Ultra. A platoon of small automated pods to ferry passengers from Terminal 5 to their cars miles away. Each pod would carry between 1 and 4 passengers with no waiting and no stops along the way. It seems like a paradox, but the fact is that these small vehicles are actually more efficient than buses and trains, because pods never make intermediate stops. That crucial insight is what spurred the system's inventor.
I'm Martin Lowson, and I guess I started this. My own career is in the space business. I was originally on the moon program, in fact.
Martin began his career in the Apollo program in the 1960s. He helped develop the Saturn V rocket that carried Neil Armstrong and Buzz Aldrin to the moon in 1969.
In fact, I can say I was a rocket scientist.
Soon after, Martin left the space program to explore ideas that were too far out, even for NASA.
What we've tried to do here is bring aerospace standards of design and reliability to what we're offering now for personal transport.
Today, Martin is about to take another giant leap for mankind. He'll take his first test ride on the system he has spent a quarter of his life developing. The stakes are high because this is also the first time Heathrow will get an operational glimpse of their $60 million investment.
It's certainly the case that the eyes of the world are on us here at Heathrow. Our belief is that there's an enormous line of people who are desperate to be second or perhaps even third. So when people can see this working, there'll be a lot of people who want something similar in their location.
For personal pod advocates, nothing less than the future of transportation is at stake, with the outcome of the Ultra System experiment.
The success of the Ultra System at Heathrow is an important event in the pod car industry. And I think the future of pod cars, at least in this era, will depend upon its success.
Martin's first ride is a simplified version of what the system will eventually be able to do. During this test, there's no other traffic to negotiate, and the pod's autonomous brain isn't connected. For now, a laptop is running the show. Once control is turned over to the pod, 4 laser sensors embedded in the vehicle will scan the guideway, adjusting trajectory and speed, while a centralized computer keeps close tabs on the entire system. The hardware and software required to run the system are quite complex. But surprisingly, the bigger challenge has been getting the guideways right. The original design was for a single-lane structure, with one-way traffic running in a loop. But the guideway layout for a one-way system would be far too inefficient. So engineers expanded it to allow two-way traffic, even though that complicated the design of the guideway foundations.
That's caused major problems because below ground we wasn't sure was there. There's a lot of old fuel lines, old water lines, and we've had to find out where they all were and in some cases divert them.
In DC, the most heavily trafficked guideways, like the route between Dulles and downtown, could be built at ground level, simplifying construction. But they would be 2 or 3 times wider to accommodate thousands of pods moving at high speed. The complexity of the system would require a dramatic leap of innovation by computer scientists and software engineers. They must design a powerful new computer network. And to fulfill the promise of perfect safety, they must endow the pods with something like intelligence, giving them flawless instincts and lightning-fast reactions. Because the margin of error is 0. And the consequences of failure would be catastrophic. When Phase 1 is complete, personal pods will link DC's Dulles International Airport to Union Station in the heart of the city. But for pods to truly overtake cars, designers must make them faster, cheaper, safer, and more energy efficient. The key is to build a robust computer mainframe to control the vehicles and coordinate a system with hundreds of thousands of moving parts. To do that, engineers could build on lessons learned at Caltrans Transportation Management Center in Southern California. Since it opened in 2002, Marco Ruano has run the War Room, where transportation managers fight the worst traffic in the country.
monitor basically traffic conditions as they occur on the system, including things like incidents and accidents. We initiate the response to these incidents and accidents. We observe flow over the system to evaluate where the bottlenecks are, where the backup, where the delay is occurring. With that, we're able to basically diagnose the freeway system here in Los Angeles, which will eventually help us to take steps on fixing congestion.
The key to the Caltrans system is a two-way flow of communication. Road conditions come in, and information to drivers goes out.
We have sensors in the pavement which tell us basically two things. The number of cars that pass over that sensor or that station, and the approximate speed at which that vehicle is going.
A computer translates raw data into a real-time picture of traffic congestion.
Generally speaking, if the map is all green, then we know that traffic is flowing smoothly. As we start to see the map change, you see maybe some yellow, some orange, we'll see that they're slowing.
The map reveals traffic conditions as communicated by sensors in the road. But the sensors only report volume, not car-to-car behavior, collisions, or other mishaps. In DC, sensors would be much more robust and would be located in the pods themselves. They would constantly relay information back to the central computer, creating a more accurate and complete picture of traffic flow. But for either system to work, it must incorporate an effective method of rerouting traffic around trouble spots. At Caltrans, this is accomplished with hundreds of message signs mounted along highways throughout the system.
So it's putting some information in the hands of the motorists so they can determine whether or not that they want to continue on that route for their commute.
Steve Halloway is a traffic manager at Caltrans.
What we do primarily is try to help people get to and from their jobs faster with as little disruption as they can due to the huge volume of traffic that we have here in the Los Angeles area.
Steve must maintain constant vigilance for anything unusual on LA freeways.
When I'm looking at the monitor, what I'm looking for is congestion. And whenever I see an area that's building up with congestion, I'll see it turn from green to yellow to orange to red. And what I do is I zero in on the area, looking at the map, and then I try to find that location and see if there's a corresponding incident, because this will give us the details of what's actually going on.
A sudden shift from green to red on one of the city's west side freeways is the telltale sign something has just gone wrong. It could be something as simple as a stalled vehicle, or worse.
Okay, right now there's an accident eastbound 60, and it's a 4-vehicle traffic collision. And so we've trained our camera 143 to look at it, and we can see the 2 right lanes are blocked in that area.
The 4-car collision creates a massive pileup, blocking the entire eastbound side of Highway 60.
Now we can respond by activating a changeable message sign so that we can tell people who are coming up to the incident that the 2 right lanes are closed there and that they can either depart the freeway or either merge over to the left to try to avoid some of the congestion.
In DC, a powerful central computer could be the key to monitoring conditions within the pod network, especially if it could communicate directly with each pod. But ceding full control to the central brain would be dangerous. A breakdown could cause chaos on the guideways.
I think that there are a couple of different problems potentially with centralized control that come to mind. One of them is that you're creating a single point of failure. The other problem is that in order to understand what a system of hundreds of thousands or even millions of cars is doing, it requires a degree of computational complexity that is just simply beyond what we have today.
On its own, the main computer would never be able to keep up with DC's pod system. Luckily, it will have help. when the pods break the shackles of central control and take charge of their own destinies. The pod system's central computer will be tasked with the job of maintaining an accurate picture of traffic conditions across the network. It will warn pods away from congestion and other hazards. But when it comes to steering themselves from point A to point B, the pods will be on their own. It sounds futuristic, but robots that operate in exactly the same way are already part of everyday life. Meet the Kiva Robot, or rather, meet the Kiva Robots. Individual members of a remarkable system that is quietly revolutionizing storage and shipping in the U.S. The Kiva system uses a fleet of robots to bring the products to the pickers, all without any human oversight.
When you look at a Kiva warehouse, it looks like chaos, but it's actually very, very carefully controlled. The major tasks, the missions, are conceived and assigned by a central server. And then the actual execution of those tasks, what specific path and decision to make, is made by each individual robot.
The Kiva bots may not look like personal transportation pods, but the problems they solve and the way the two systems solve them are remarkably similar. In the Kiva system, incoming orders enter the central computer, which maintains an accurate map of the entire warehouse.
The central server knows where every robot is at every moment. In fact, the central server knows where every movable shelf is at every moment, and every item on that shelf at every moment.
In the same way, the central computer in the pod system would know the layout of the city and the location of each pod. It would dispatch a pod to pick up a rider, and then tell the pod where the rider wishes to be let off. The central server would never actually control the movement or steering of individual members of the fleet. Instead, it would act like the server in the Kiva system, using the information it has collected from its units in the field to issue orders and offer general guidance, but always leaving it up to the individual to figure out how to get the job done.
So the central server handles what we call high-level tasks. It decides what mission to send which robot on. It decides which areas of the warehouse are too congested to travel through. But the individual robots make individual decisions about what turns to make or how to avoid an obstruction.
Not only that, but the robot also reports that obstruction to the central system, which then lets the rest of the fleet know to avoid the problem area. The result is behavior that can seem intelligent and purposeful, something that can make human coworkers regard the robots a bit warily. But not to worry.
Well, we actually think that the robots are not evil. In fact, individual by individual, we find there are fewer evil robots than evil people. That's the statistical sample that's been taken by our research department.
This mix of central and local control means that the system is completely scalable. There's no theoretical upper limit. The DC pods will require much more sophisticated control than the Kiva robots. The pods will move in tight clusters at high speeds. To avoid collisions, engineers will teach the pods behaviors common in the animal world.
When you watch birds flying, there isn't a single pilot in the front that's telling people go left, go right. They somehow manage to all fly together in a formation. The individual birds follow very, very simple rules. Go in the general direction that your neighbors are going in. Avoid bumping into anyone, and try to get close to them without bumping into them.
Scientists call this emergent behavior. It's when a group purpose seems to emerge from the apparently random activities of individuals.
Each ant, as they're going back and forth, they're laying down a chemical trace known as a pheromone. Very quickly, the ants will create almost like a highway to the nearest food source.
The Kiva robots exhibit emergent behavior based on a very simple set of rules. The pod's rule set would be much more sophisticated because the urban environment is more complex than that of a warehouse. The basic principles would be the same. Engineers are confident that they could teach pods to navigate around obstacles more safely than cars, while working together to find the most efficient routes to their destinations. As pods are deployed into DC and other cities, they would gradually make the car obsolete. But that wouldn't necessarily spell the end of car companies. Manufacturers already see the writing on the wall, and they're spending billions to develop the smart technologies that pods will require.
We don't realize it a lot of times, but a lot of the cars are already taking over some of the functions that we think that we're controlling ourselves.
This experimental car uses an array of radar, sonar, and video cameras to sense and avoid disaster. And it can even overrule the driver to avoid a collision. Like the pods of the future, these experimental cars can also communicate with the road.
What we have is a roadside unit that's actually in the intersection that's talking and sending signals out to the vehicle. And as the vehicle approaches the intersection, there's that communication of, is the signal turning to a red light?
Prepare to stop.
And if it is, it actually can bring the vehicle to a stop when the signal turns red.
But these modest systems all share a fundamental weakness: the driver.
Something like greater than 90% of accidents are due to human error. And so they are kind of the variable in the equation. If we can bring technology like autonomous vehicles, then we can remove that source of error and save an awful lot of lives and money and, do an awful lot of good.
The final and perhaps toughest obstacle for the pods to overcome will be wresting the wheel out of human hands. If engineers can teach pods to drive themselves, the end of the auto as we know it will be at hand. At least that's what Chris Urmson hopes.
Okay, so we're going autonomous now.
He's a professor of robotics at Carnegie Mellon University, where he's developing the world's most sophisticated self-driving car. Meet the Boss. Boss uses an arsenal of 19 sensors, GPS, and a powerful computer to drive without any human input. Boss maintains a detailed virtual map and constantly takes stock of its position and its progress towards its goal. But that's no problem compared to actually driving. So natural for a human, so difficult for a computer. Even the most basic maneuvers are surprisingly complex. Simply stopping at an intersection requires highly choreographed communication between Boss's internal GPS, its sensor array, a detailed digital map of its environment, and of course, the computer which is controlling the steering wheel, the gas pedal, and the brake. Add another car into the mix, one controlled by an unpredictable human, and the situation becomes exponentially more complicated. Take the common problem of passing. Chris has been working hard on this maneuver, and it has proven to be challenging. In this demonstration, Boss must decide whether to pass, when to pass, and how to pass.
So today we're out testing the dynamic passing maneuver. So this is the case where you're on a two-lane road, both lanes go in the same direction, and another vehicle is out in front and slows down or isn't driving as quickly as you want to drive. So you have to come up behind it, understand that vehicle is driving slower than you, pop out of the other lane and pass it safely. Now, Boss maybe doesn't do that like a person would. It doesn't drive as smoothly around them. It tries to make the lane transition as quickly as possible because that's one of the areas where it's concerned that people don't understand what's going on around it. So if it can make that decision quickly and execute it quickly, then the other vehicles don't have much time to change their mind and do something differently.
Riding with Boss can sometimes be hair-raising as it guns its way into the oncoming lane and tries to get to safety as quickly as possible. Chris and his lab are now working out algorithms that will make riding with Boss more comfortable. But even in its unfinished state, BOSS is already more reliable than a human in most driving tasks. It's an incredible accomplishment that points the way to a future of self-driving vehicles, bringing benefits once reserved only for the chauffeured elite.
In the U.S., the average commute is something like an hour and a half a day. That's time where you're stuck, wasting your effort, holding the car in a lane, not doing much other than getting between point A and point B. If we could make the cars be able to drive themselves, we give you back that time. You could sleep, you could read a book, you could catch up on email. You could do all the stuff you do in a car right now, like, eating your breakfast and putting on your makeup, without it being dangerous.
But most important, a sensitive, highly communicative pod could end the slaughter on the world's highways that claims over 1 million lives each year and costs billions of dollars.
Worldwide, it's something like 1.2 million, so it's a tremendous loss of life. The financial cost of these accidents is, and not just fatalities, but accidents, is 3% of the world's GDP.
And the savings wouldn't end there. The pods themselves will be far cheaper to build than today's cars, and will share many design similarities with the Kiva robots. Because pods, like the robots, will be so adept at avoiding accidents, they won't require the heavy steel cage that autos require to protect passengers. Pods will be built out of lightweight plastic or composite materials. And like the Kiva, the pod will be powered by a pair of efficient, high-torque electric motors, eliminating the far heavier internal combustion engine. The largest Kiva robot in production is rated to carry a 3,000-pound load, plenty of power for a pod. And when their batteries run low, they are smart enough to drive to the nearest self-charging station to top off with electricity from the power grid. Despite the gains in efficiency and safety, designers know that it will take a tremendous act of political will to bring the pod system into being. But DC already spends more than $1 billion a year on new roads. And it's a losing battle. With lightweight pods, the city can solve the construction problem by building overhead elevated express routes, cheaper than roads. These elevated guideways would move vehicles using magnetic levitation, a lightweight and nearly frictionless electric propulsion system. Elevated guideways would allow pods to bypass the most congested areas of the city. Streets would once again become the pedestrian-friendly boulevards they were intended to be. With the lightweight infrastructure in place, the city's all-electric pod system would be the greenest form of mass transportation ever devised. Traffic fatalities would drop to near zero. Fire, safety, and police vehicles would be granted automatic right-of-way, cutting emergency response times by almost 80%, which could be of critical importance in our nation's capital, where terrorism is a constant threat, and the pods themselves could present a tempting target. Personal pods would transform Washington, D.C.
Well, pod cars give us the opportunity to fundamentally change how we design our cities. We want to get back, I think, to walkable communities that aren't dominated by the needs and the conditions of using an automobile to move from one point to another.
Self-driving pods would lead to dramatically reduced commute times. And during off-peak hours, excess pods could be diverted to hangars for recharging and maintenance. But their ability to travel anywhere and everywhere at the touch of a button could make the system a tempting target.
Transportation systems are certainly targets for terrorist activities. There are lots of people. They are very open systems, so it's easy to get in and out.
In Washington, D.C., a coordinated attack on the pod system would terrorize the city. But most attempts could be easily thwarted. An assault on the guideway system would prove only a minor disruption due to the redundancies in the guideway infrastructure and the pod's own senses. A computer virus intended to knock out the central mainframe would cause only limited damage, since each pod has its own computer brain and the ability to communicate with other pods. But with the system running pods close by both the White House and Congress, just blocks apart, an attempt to use the vehicles as guided bombs to wreak destruction could paralyze the entire country. But luckily, the very automation that could trigger a plot to turn pods into bombs would also be the ultimate safeguard. Each vehicle would be equipped with a hidden layer of security, a device capable of sensing nearly any kind of explosive. Regina Dugan is an expert in the chemistry of bombs.
The unique thing about explosives is that they're sticky, so they tend to adhere to surfaces and hands, and they tend to stick around. And it's difficult to remove the evidence of handling explosives. In that bomb-making facility, it would be on hands, it would be on my clothes. If I tried to remove it from my hands, as soon as I touched another surface, I would recontaminate my hands. So it is, in fact, very difficult to remove all evidence of contact with explosives.
Regina is the president and CEO of Red X Defense, which produces a fluorescent detection technology that can sense and even identify trace levels of high explosives.
This technology allows us to see trace explosives for the first time in our environment. We can actually visualize that these particles are present on a surface.
Each pod could be equipped with technology to scan its own interior before every ride. If it detected a bomb, it could react by locking its doors, sending a signal to the system to clear all other pods, and then moving itself to a designated safety zone. Compared to the threat posed by a bomb stashed in an anonymous parked car, the pods would be vastly safer. DC's traffic problem is big, and the solution will have to be bold. Building the world's first pod city would take epic engineering and uncompromising vision.
50 years ago, we couldn't have built these types of systems. But with advances in material science, computer technology, and manufacturing, these systems can be built, and they must be built. And I would put forth the idea that in the 21st century, the network that will come to dominate the United States and the world will be pod car networks which more effectively serve the needs of our commerce and the movement of our people. The future of transportation depends upon it.
In the end, the personal pod wouldn't just rewrite the rules of the road in Washington, D.C. It would transform the world forever.